Hello guys, I'm back. So I'll just stop a while ago in the energy in terms of the ideal gas law. So we have the formula of energy, the capital E is equals to 3 halves nRT. Okay. Okay. This one. Capital E is equals to 3 halves nRT. So in this equation, we are considering the kinetic energy, okay, the movement or the motion of the particles of gases. That's why we derive this equation, okay, like that. So usually the units of energy is joules, something like that. Okay, do you remember the joules? Okay, so in relation to that also, we can use a conversion factor is equals to 1 calorie. 1 calorie is equals to 4.184 joules. Like that. 1 calorie is equals to 4.184 joules. Okay, that this is energy deriving to the ideal gas law. Okay, going back to ideal gas law, it is a general gas equation. So we have the pressure times the volume is equals to the number of moles or the amount of substance times the R, which is the constant or ideal gas constant or the universal gas constant times the temperature. It could be represented in this way. Okay. With ideal gas law, P this one. Okay, this is an ideal gas law. Okay, PV and RT. Hello guys. P is the pressure of the gas. V is the volume. Okay. N is the number of moles or the amount of substance referring to a gas. R is the ideal gas constant or the universal gas constant. Okay, it's the same. Okay, and T is the temperature in Kelvin. Okay, it's not in Celsius, so this is standard. Every time you encounter a problem regarding ideal gas law, so it is not Celsius, but it is Kelvin. So to convert that, if the given is Celsius, you have to use the formula Kelvin is equals to degrees Celsius plus 273. Okay. Okay, this one. Temperature is equals to Celsius plus 273. Okay. So in taking up an engineering course, you have to develop a solid stack knowledge so that you will never found difficulty to encounter complicated problems in the future, because sometimes, especially me, if I don't encounter uh, uh, problems that are most commonly discussed by our instructors before, I will keep on searching or researching in the library. Okay, so like that. And sometimes we can derive uh, formula through that also. So deriving a formula or an equation out of those basic given formulas or equations, then it is more good, because sometimes there are complicated problems that they mixed the basic and the complicated one in one single problem. Then if you have the basic formula, then you can connect that one, connecting the dots, and then you can solve what is being required in the particular problem, right? Like that. So I think I cannot give a practice problem of the ideal gas law because it will take time too much if I will do that. Okay? So, like that. Okay. Finish to that ideal gas law or the general gas equation. Okay. Like that. So it will determine a good approximation of the behavior of the gases under certain conditions. Okay, but it has limitations. Okay, as I said earlier, it does not consider or it neglect the molecular attraction and molecular sizes. Okay, in ideal gas law. So, but in a real gas, it's being considered there, the molecular attraction, the molecular size. And then this ideal gas law is applicable at high temperature and low pressure only for monoatomic gases. And now you are now alert what are those monoatomic gases comes in your head now. So you can research also. Okay, like that. Now in this equation, R, it's a mystery. How can we solve R? Since it is a constant, supposedly you should memorize it. Okay? If you're taking engineering course, but if you are not an engineering student, okay, then you have to do the derivation. So actually, this R, or the universal gas constant or the ideal gas constant, is equal to the product of Boltzmann constant and the Avogadro's constant. The product will be the R, and we don't have to go in detail what is the Boltzmann constant and what is the other one. Okay, Boltzmann constant. Okay, the other one, which is the Avogadro constant. So what I remember in our general chemistry, the Avogadro's constant is 6.023 times 10 to the 23. Okay, like moles per molecule, something like that. Like this. Avogadro constant 6.023 times 10 to the 23 moles like this. 6.023 times 10 to the 23 is Avogadro's constant or number. Correct me if I'm wrong. This is based only on my stock knowledge. Okay, so this will be used multiplying this to the Boltzmann constant, and then we can get the ideal gas constant or the universal gas constant. Okay, so assuming we have another product R, so we will use the, okay, this one, the most common one in solving the ideal gas problems, 0.0821 letter. This one. Okay guys, this one is the universal gas constant or the ideal gas constant, is equal to 0.0821 letter atmosphere per mole Kelvin. So be careful in using your PV and RT, okay, because you have to agree with the units And if the units will not agree, you have to convert that one. So I will give you basic conversion regarding atmosphere or the pressure, because R involve pressure. Okay, ATM is the pressure, right? So this liter mole, liter per mole per mil usually will not vary, but the most of the times vary is the pressure. So sometimes you can have it liter, for example, liter mmHg, which is Kelvin, liters kilopascal over mole Kelvin. So I have to give you the basic conversion about pressure. So this is very important also, not only in gases but for the transport of fluids and liquids also. Okay, so we need to determine the pressures like that, the volume, the flow, something like that, and we have this conversion. Okay, I will never discuss everything because it will take a longer time. Okay, pressure. Okay, 1 atmosphere or ATM is equals to 760 millimeters mercury. Okay, take note that one. Later I will be showing you the paper. Okay, 1 atmosphere is equals to 14.7 psi. Okay, 1 atmosphere is equals to 101.325 kilopascal. 1 ATM is equals to 101,325 pascal. So 1 ATM, so 760 torr. Okay, 1 bar is equals to 14.7 psi. Okay, these are the conversion factors of pressure. Okay, this will help a lot also if you are working in process plants. Then you have to determine the pressure, like that, the technical parameters of the fluid flow, gaseous flow. If you are a process engineer like that in a certain manufacturing plants or operational plants, something like that, especially if the industries are chemical industries, power plant industries like that, or nuclear power plant, something like that, that deals usually with gases, something like that. Okay, so these are the, okay, 1 ATM is equals to 760 millimeters mercury. 1 ATM, 1 atmosphere, 14.7 psi. Okay, 1 ATM is equals to 101.325 kilopascal, or 101,325 pascal. 1 ATM is equals to 760 torr, and then 1 bar is equals to 14.7 psi. Okay, so this will be your conversion factors that is helpful to solve in this equation, or the general gas equation, or the ideal gas equation. Okay, like that. Okay, so the ideal gas law also, so it is discovered or stated by Benoit Emile Clapeyron in 1834. The combination of the empirical Boyle's law, okay, Charles' law, and the Avogadro law. Okay, it's a combination of that laws, and then we can come up with the ideal gas law. Before it has became an ideal gas law, it is a combination of the empirical law of Boyle's law, Charles' law, and Avogadro law. Okay, like that. So, si Mr. Benoit emailed Clapeyron in 1834. He stated that one, or he discovered that one. Okay, like that. So I will, this one, Mr. Benoit. Okay, email Clapeyron. Okay, this guy, Benoit emailed Clapeyron in 1834. He stated that it is derived for the combination of uh, Boyle's law, Charles' law, and Avogadro law, the ideal gas law or the general gas equation. That's theory. This is theory, okay? Basic theory is the one, okay? Like that. So, Boyle's law, plus Charles' law, plus Avogadro law. Okay? So these three laws actually under ideal gas law. Before we come up to the formula of PV and RT, okay, this has been combined. And the one who stated is this Benoit, Emile, Clapeyron in 1834. So the Boyle's law, as we can remember in our high school chemistry, it should be the pressure times the volume, okay, is equals to constant, okay, wherein the temperature is constant, okay, like that. For the Charles law, equals to the volume over the temperature is equals to the constant. So meaning to say, the pressure is constant, okay? And for the Avogadro law, will be the volume divided by the number of moles, or the amount of substance, in which temperature and pressure are the constants. So there are two constants in Avogadro law, okay? That one, combining that all, we can arrive the PV and RT. So if I have more time to do that, we can derive that through mathematical equation, and we can arrive the ideal gas law formula. But I will give you the formula of Boyle's law. Okay. So, Boyle's law, pressure 1 times volume 1 is equals to pressure 2 times volume 2, in which temperature is the constant, okay? For the Charles law, we have volume 1 divided by T1 is equals to V2 divided by T2, so pressure is the constant. Avogadro. So this is the Avogadro law. volume divided by the amount of substance is equals to constant, or constant represented as Na. Okay, and then pressure and temperature are the constants. So combining this all through derivation, we can get this formula: PV is equals to nRT. So that will be about ideal gas law, guys. So tomorrow I will be discussing the rest, okay, of the topics here, okay, and some solving of problems, so that it will give you an idea if you're working on process plants, power plants, nuclear plants, like that, and it will be useful also, okay, like that. Okay guys, that would be enough. It takes me 21 minutes to do that. Oh my god, if you really discuss the systematic way of doing it, then it will take a lot of time, okay, like that. And by the way also, we have the formula: pressure times volume is equals to nRT, the general gas equation or ideal gas law, right? And then we will examine each of the property, or let's say the variable. So P has also the formula of force over area, okay? Then V has also the formula in terms of density, okay? Density equals to mass over volume. Okay, the volume is equals to density over the I will write, I will not memorize it because it will complicate me. Okay, density, okay, density, okay, and then okay, this one, density mass over volume, and then you can determine also the value of V, okay, and you can insert that in the PV and RT also, okay, and then equals to nRT, like that. So there are problems that they will mix the area of the pipeline in which the gas will go there, and you can compute also the diameter, because you have the formula: pressure equals force over area. So area, usually the surface area, right? Pi d squared over 4. And somewhere that along the way, it will be also incorporated in the problem of the ideal gas law, in which the students will be confused, because sometimes the instructors will not go deeply on that particular, okay, particular formula, because it is understood that that's already a basic foundation when you are in high school, like that. It was discussed, right? Even in elementary, it was discussed that density equals the mass over volume. So when going to the ideal gas law, the instructors will never say anymore density is equals to mass over volume, but when they solve it, they will automatically substitute the given values, okay, and the students will just analyze, it came from the density equals mass over volume, or pressure is equals to force over area, since ideal gas law has pressure times volume is equals to nRT, and you have to substitute one by one, okay, and then agree with the units, and you can solve the correct answer for that, okay. But do not confuse with the units, okay. Units must be very very important in solving problems in ideal gas law, not only in the ideal gas law, but anything in mathematics, algebra, like that, chemistry, stoichiometry, chemical calculations, like that, energy problems, heat problems, thermodynamic problems, like that. So we should be careful for that, agreeing the units. So the first thing to do if there is a problem solving is that you have to analyze the question, okay, and then number one is what is being required. We have to analyze, and then what is being required, and that, for example, volume, then you have to think for the formula of the volume, okay, like that. And you have to list the given, through that given you will plug in to the formula, and then agree the units, okay. And never be afraid that there are still basic formula under that variable within that formula equation that you are be using. Example, the ideal gas law. P, pressure times volume, is equals to in RT. Pressure is equals to force over area. Volume is equals, can be derived by the equation density equals to mass over volume. Okay? Or it could be also from the work formula. You remember that one? So work is equals to force times distance. Something like, okay? Since there's also force there, it's related also to pressure is equals to force over area. Okay, and then you will attach those uh, basic formula, and then you can come up with a derived uh, new formula, okay, connecting those basic formula, something like that. And it's your initiative already, because it's understood to be the effort of the students to do that, okay. It's not really the sole responsibility of the instructors and the mentors to spoon feed for you to do that. Okay, you have to research, and you have your own initiative to refer to different books in the library, or you can go to the net, okay, like that. Okay, guys, that would be all. Talking about ideal gas law or the general gas equation, all about ideal gases, something like that. I hope you understand a little bit. I know if you are not an engineering graduate, or if your course is not related to science, you will never found interest to listen with this type of vlogging. But I'm just sharing to you the academic information, or a little academic information regarding gases, ideal gas. So see you soon for another topics in chemistry, but I think I will go to solids and liquids. But before going to do that, I still have to continue in gases, okay? Because gases, or gas as a phase of matter, is very interesting for me, okay? Like that. Thank you so much for listening. Babush, bye bye.